Multi-camera parallel tracking and mapping, or MCPTAM, is a set of ROS nodes for running real-time 3D visual simultaneous localization and mapping using multi-camera clusters. It includes tools for calibrating both the intrinsic and extrinsic parameters of the individual cameras within the rigid camera rig. MCPTAM is an extension of the PTAM software from ISIS Innovation. A camera cluster is a set of any number of cameras in fixed positions and orientations with respect to each other. They offer the flexibility to arrange the cameras into configurations that have large baselines and a wide collective field of view. This has several advantages over other camera configurations, including high accuracy tracking, effective use of available image pixels and computing resources, and the ability to maintain observations of the trackable regions in the environment. Several modifications and improvements have been made to the underlying PTAM framework. MCPTAM is able to use any number of cameras arranged into the cluster configuration. Using multiple cameras allows for full global scale recovery of reconstructed map and camera motion. An omnidirectional camera model allows for the use of fisheye lenses with greater than 180-degree field of view. The system is fully integrated into ROS and has a redesigned mapping optimization backend running G2O. Mapping and tracking initialization is immediate from the first set of camera frames for cluster configurations both with and without overlap in the camera fields of view. The pose tracking and map building operations can be run as separate processes and executed on different machines to allow for full client-server operation. The MCPTAM system can be used for any visual tracking tasks by following the simple setup process. In this example, the camera cluster is composed of 3 cameras with fisheye lenses, all fixed to the handheld rig. For each camera within the cluster, the camera intrinsics, that is, the image center and distortion model, are found using the camera calibrator node. By observing a checkerboard from several viewpoints, the camera parameters are automatically computed. This process is repeated for each camera within the cluster. MCPTAM uses the known positions and orientations, or extrinsics, of the cameras in the cluster to generate the environment map and track the motion. The camera extrinsics with respect to the first camera are found using the pose calibrator node. Starting with the designated first camera, each camera is shown a checkerboard pattern with known dimensions situated in the environment. Once initialized, the system begins to generate a map as the next camera is brought around to look at the checkerboard. From this, each camera's pose is found, and they start to track and contribute to building a single map. Once a large enough map has been built and each camera is initialized, the extrinsics are computed. With the intrinsic and extrinsic calibration of the camera cluster resolved, the MCPTAM node is able to quickly and accurately construct a map of the environment and track the current cluster's 3D position and orientation in real time. The tracking and mapping processes begin running in parallel immediately. MCPTAM has been successfully applied to several robotics applications, including a quadrotor UAV using the MCPTAM real-time pose estimates for feedback to the position controller. The system is able to perform fully autonomous takeoff, waypoint flight, and landing operation using only the vision feedback and onboard inertial sensors. The system is able to successfully operate in both indoor and outdoor environments. The full 3D position and orientation estimates allow the quadrotor system to fly in high wind. Additionally, the large collective field of view of the camera cluster allows the quadrotor to operate in urban environments where a lack of texture in some areas can make visual tracking difficult. MCPTAM is released under the GPL3 license and is available for download at GitHub.